Hello, welcome to the discussion on the time value of money. I think you'll find that this is one of the most important basic foundational concepts that we will use in our course because pretty much everything we do in the course beyond financial statements will actually build on the time value of money. So let me go ahead and get started and give you an introduction into the tools of time value of money. So this is an example of, let's say that you won the Powerball lottery, and so you're entitled to $73.7 million in payoff money. So, or prize money, I guess. So you can get it one of two ways. If you want your money in a lump sum, they're only going to give you $41.4 million. If you choose to get the money spread out over a 25-year period, that's how you get the $73.7 million. You would get just under $2 million a year every year for 25 years. So your dilemma is to choose, would you rather have the $41.4 million today or the roughly $3 million a year every year for the next 25 years? Well, let's say that you know that if you were to receive that $41.4 million today, you have a guaranteed account that gives you 6% interest, let's say, and that is a guaranteed interest rate. So the way you would figure which way you're better off is you'd want to bring both of those amounts into the present value, discounting at 6%, which is your opportunity cost, it's your guaranteed rate of return, and then compare the two present value figures, and you would choose the one with the highest present value. So for instance, that $41.4 million that you received today is already in present value, so you wouldn't have to do anything with that. But then what you would do is take the $2.948 million at the beginning of each year for the next 25 years and discount those numbers back at 6% for each year and sum them up. And then whichever number is larger, the number you would get when you sum up that what we call annuity, that $2.948 million annuity, or the $41.4 million, that would be the choice you'd make, the larger of the two. So that's what I'm going to show you here in the upcoming slides, is how exactly would we do that. First of all, it's important to know what determines value, and this is the first rule of finance, and we will be using this rule over and over and over again. The first rule of finance is that the value of any asset is equal to the present value of the cash flows you expect to get from that asset. So it doesn't matter what the asset is. If the asset is a bond, then the value of that bond is going to be equal to the present value of the cash flows you expect to receive from that bond. If it's a stock, the value of that stock is equal to the present value of the cash flows we expect to receive from that stock. If it's rental property, the value to you of that rental property is the present value of the cash flows you expect to receive from that rental property. Of any investment project that your firm invests in, the value of that project to them is equal to the present value of the cash flows they expect to receive from that project. So that is a rule that applies to all types of assets. And so we'll be building on that rule throughout the course. So how exactly do we find present value and future value? Well, let's start with just a simple future value problem. Suppose you have $100 and you deposit it in a savings account that earns 5% interest. How much would you have at the end of 1 year? Okay, so you can see here that I've got the future value at the end of 1 year is equal to $100 plus, here's the interest, the 100 times the 0.05 that you're going to collect over the course of the year, so that by the end of the year you'll have $105. You have your $100 principal plus your $5 interest. What if you take this $105 and invest it then another year, so that your money sits in the account for 2 years? Then that $105 is going to earn 5% interest, so that at the end of the second year you'll actually have $110.25. We could have found the future value by taking the present value or the principal amount, present value is the amount we're investing, and multiplying it by 1 plus R, R represents your interest rate, twice if we wanted to find the future value in year 2. So again, the future value in year 2 is equal to the principal or the present value times 1 plus the interest rate times 1 plus the interest rate, or the present value times 1 plus the interest rate squared. So in our numerical example, the future value of this $100 at the end of year 2 is equal to $100 times 1 plus the interest rate of 1.05%, and then we have a total of $110.25. So this is the calculator version of future value. The future value at the end of year n is equal to the principal times 1 plus the interest rate raised to the nth power, however many years out you want to go. If you prefer to use your present value, future value tables, for right now, that is fine as well. So we've got the future value in year n is equal to the present value times the future value interest factor, and you would find your future value interest factor by going to table 1 of the handout tables that I gave you, and R is the interest rate you would look. So you'd move across the top of the table till you find your interest rate. In this case it was 5%, and move down into the body of the table, go down the column until you go down 2 periods, 5%. So R is 5%, N is 2 for 2 years, and that's where you would find your interest factor. And if you look it up, you'll see it's 1.103 in your table because it truncates at the 3rd decimal point. Present value is just the opposite of future value. That's taking a future sum and discounting it back to today to see what it's worth today. So here what we would do to find the present value, we take the future value and divide by 1 plus the interest rate. Now when we're talking about present value, we usually refer to this R now as the discount rate. So when you're computing future values, you're compounding by the interest rate, and when you're finding present value, you are discounting by the discount rate. And then again, here is the formula version for the calculator, or you can use the handout table 2, and you find your present value interest factor by going to the appropriate interest rate and then move down the column to the appropriate number of years, and then that will give you your interest factor, and you can just multiply. So let's go ahead and work through an example. Let's say you're offered the alternative of receiving either $127.63 at the end of 5 years or X dollars today. You know that if you deposited the money in the bank account, you would receive 5% interest. What value of X would make you indifferent between X dollars today and the promise of $127.63 at the end of 5 years? Okay, so this is a present value problem because they're asking you, okay, you've got a sure thing 5 years from now of $127.63. If you were to receive instead a lump sum, this is basically very similar to that lottery opening problem that I had. If instead you were given some lump sum, what lump sum would make you indifferent between receiving, the X amount of dollars today or the $127.63 5 years from now? And so what we would do is discount that $127.63 at the interest rate, in this case the discount rate, because that's a sure thing for you. You have a bank account that's going to give you 5% interest, and this money would occur, this $127.63 would occur 5 years from now. So we want to discount it back to today to see what it's worth today, and we find out when we do the math it's worth $100. Or you could use a table, because that's the calculator version. If you use the table, again, you would go to table 2, and you have the $127.63 multiplied by your present value interest factor of 0.784, and that gives you the $100 present value amount. Okay, and again, I got this 0.784 by moving across the top of the table to get at the discount rate at 5%, and then move down the body of the table until I found 5 periods or 5 years. I'm going to move to a laser pointer here, so I have that to use. Okay. Now, future value of an annuity. An annuity is a payment or a receipt. Okay, it can either be an inflow or an outflow. So let's say it's a receipt. It's a receipt or an amount that you would get of the same amount. So in other words, the payment that you receive cannot change from year to year. So it's a fixed amount for a specified number of periods, and then it ends. Okay, so that would be the definition of an annuity. So oftentimes, when people retire, they purchase retirement annuities where they receive some fixed amount every year. So how do we value an annuity? Well, this is where your tables 3 and 4 come in. We have what's called an ordinary annuity, and the example I use here is a promise to pay $1,000 each year for 3 years is a 3-year annuity. If the account, let's say, pays 4% interest, the question is how much would that annuity be worth by the end of year 3? Okay, so this is a future value of an annuity problem because we're trying to figure out what is that annuity worth 3 years from now. What lump sum is it worth? Okay, so let's say you have your 3-year annuity and you're going to receive $1,000 at the end of year 1, end of year 2, and again at the end of year 3. And each time you receive a payment, it's going to earn 4% interest each year. So the first $1,000 you receive at the end of year 1 is going to earn 4% interest for 2 years until we get to the end of year 3. So I can go to table 1 and look up that interest factor. So go to table 1 and look up 4% for 2 years. That gets us from the end of year 1 to the end of year 3. And you'll find the interest factor to be 1.082. So when you multiply, we find out that this $1,000 will be worth $1,082 by the end of year 3. The next $1,000 payment will be worth $1,040 because you receive it at the end of year 2, and it will sit in the account for 1 year until you get to the end of year 3, and will be worth $1,040 then at the end of that year. And then the third $1,000 payment doesn't have any time to collect interest because you don't receive it until the end of year 3. So now you sum these up to find out what is your total amount sitting in your account at the end of year 3, and you find out you have a total of $3,122. Okay, this is one way you could solve the future value of an annuity, but as you might guess, if you had a 20 or 25 year annuity, this would get rather monotonous. So fortunately, we do have a shortcut version, and if we go to the annuity table, what it does, and your annuity table, the future value of an annuity would be table 3. We could use this formula to solve the problem, which is what I've done here. So the future value of an annuity is equal to the annuity payment times the future value interest factor of an annuity, which is found in the handout table 3. And I don't know that the handout table matches up in order, in the same order as your present value tables at the end of your book. Sometimes books will do present value tables first, and then present value of an annuity, then future value tables, future value of an annuity. So that's why I give everyone the handout and just refer to the handout so I know everyone's using the same tables, and that's what my table numbers are reflecting here. So the future value of an annuity is table 3 in your handout. So what we would do then is we would go to table 3 and we look at 4% for 3 years because the interest rate was 4, and we want to find the future value at the end of year 3. And we find that that interest factor is 3.122. So now we take our $1,000 payment, multiply by 3.122, and we find out that the future value of the annuity is $3,122. All right, what about the opposite? What about present value of the annuity? So I take the same example, and this time we'll assume that the discount rate is 4%. And so I'll go through, and again, if we receive the first $1,000 at the end of year 1, the next one at the end of year 2, and the next one at the end of year 3, I can discount those amounts back to times 0. Okay, I'm discounting here to times 0. And so if I go to my present value table, which is table 2, I can find my present value at 4% for 1 year, and that present value interest factor is 0.962. Here it's 4% for 2 years, and this would be 4% for 3 years, taking that $1,000 back 3 years to time period 0. So when I multiply, this $1,000 becomes 962 because it's worth less today, right, than it is a year from now, because you can invest it today and earn interest. In fact, if we invested it today at 4%, we'd have exactly $1,000 at the end of year 1. This $1,000 is discounted back 2 years at 4%, so now it's worth $925, and this one will fall in value to $889. So the present value of this annuity is $2,776 even. Likewise, we have a present value of an annuity table, which is table 4, that will allow you to conduct this calculation in one fell swoop. So I'll show you that. Okay, and here it is. We have the present value of the annuity is equal to the annuity payment times the present value interest factor of annuity, and I go to table 4 to find that interest factor. And so at 4% for 3 years, in table 4, you should find that interest factor to be 2.775. And so when you multiply, we actually get a rounded dollar amount of $27.75. But sometimes in some of these problems, I'll just round to the nearest dollar. What happens when you have more frequent compounding periods? You know, oftentimes you'll see where an investment might advertise that it pays interest semi-annually or quarterly. So we can still use the same formulas we've talked about thus far, but we do have to make an adjustment. And the only adjustment we make is we incorporate what I'm calling M here, where M is equal to the number of compounding or discounting periods per year. So to go through an example, suppose you have $1,000 in a bank that advertises that it pays 6% interest semi-annually. How much would you have in 1 year? Okay, so the formula then would be, we want the future value at the end of 1 year. Okay, so that's equal to the principal amount or the present value. And then normally we would just have times 1 plus the interest rate raised to the nth power. But instead, since this is a semi-annual, since it's going to be compounded semi-annually, we've got to take that annual rate, which is 6%, and turn it into a semi-annual rate. So the number of compounding periods per year for semi-annual interest would be 2, right? So M is equal to 2. And then, so we take the interest rate and divide by 2 and take the number of years and multiply by 2. So you'll see here our formula changes slightly, where we have our $1,000 principal times 1 plus the interest rate divided by M, or 2, raised to the M times N power. We're only compounding for 1 year or 2 6-month periods. So once I make the adjustment, then I go through and do the math, and I get $1,060.90. Now, I will point out that I did this with the calculator. You could do this with the table as well. Here you would go to the future value table, but your interest rate you would look up, you'd have to take the interest rate and divide by M, so you would look up 3% for 2 periods. Okay, and then you would get the same answer if you found the future value interest factor in table 1. Notice too that, you know, as you would expect, since you're getting interest on interest, you get a little bit more money at the end of 1 year, $1,060.90, as opposed to if it were only compounded annually, you wouldn't have a chance to earn any interest on that first 6 months interest, so you would only get $1,060. So what if it were compounded quarterly? Well, the only thing that would change is m would be equal to 4. So now you'd have to take that 6% annual rate and divide by 4, and take the number of years you're compounding out and multiply by 4. So now you're looking at 1.5% interest quarterly for 4 quarters, because we're just doing 1 year again. And that would come out to be $1,061.36. What about monthly compounding? Okay, well, this would be 12, right? So you divide by 12. So pretty simple adjustment to allow for that more frequent compounding. Same type of adjustments required for more frequent discounting. So here's our formula for present value with the more frequent discounting. Again, same adjustment, taking the interest rate, dividing by m, number of discounting periods per year, and taking n and multiplying by m to get the number, again, of discounting periods per year. So let's look at an example using present value. Okay, so let's find the present value of $8,000 at 8%, discounted annually, semi-annually, and quarterly for 3 years. Okay, annually is a straight present value problem, and I just did it all here using the calculation version, but again, you can use the tables, and I'll explain that as we go through. So the present value, we're discounting back 3 years, of $8,000. We've got 1 plus the interest rate of 8%, raised to the 3rd power because we're discounting back 3 years, and so we get 8,000 times 1 point, or I'm sorry, not times, divided by 1.2597, and that gives us a present value of $63.50.66. Okay, if you wanted to use the tables to get this $63.50.66, what you would have done is take the 8,000, go to table 2, and look up 8% for 3 periods, 3 years, and look up that interest factor, and then multiply it by the $8,000, and you would get the same answer. There could be a few cents off because of rounding, a few cents difference because of rounding, because you do get a little bit more rounding error with the tables, but it would be close enough. Okay, what about semi-annual interest? Well, this is where m comes in, so we make our m adjustment. We have 2 of them. We've got to take the annual interest rate and divide by m and the number of years and multiply by m to get the number of 6-month periods. So now we're working with a semi-annual rate of 4% for 6 6-month periods, and we get a present value of $63.22.50. Again, if you wanted to use the present value tables, you could, but you would be looking up the interest factor at 4% for 6 periods, and rather than dividing, you would multiply by that present value interest factor. So it'd be 8,000 times the present value interest factor in table 2 at 4% for 6 periods, and you should get something really close to the $63.22.50. Quarterly discounting, we're going to take the interest rate and divide by 4 and the number of years and multiply by 4, because we have 4 discounting periods per year. So now we're looking at 2% for 12 periods, and that gives us $63.07.95. So notice the more frequent the discounting periods, the smaller is your present value each year. All right, many times, and in fact, I'd actually say most of the time, when we really get into applying these tools, we're going to be dealing with a series of receipts that are not the same. So we will not, there may be times when we're dealing with annuities, but there's lots of times when we're not dealing with annuities. So how do we deal with that? Well, here I have an uneven series of payments. So, and I put it on a timeline, so time period 0 represents today again. And so this is an investment. I'm going to go ahead and frame this as an investment type problem, since that's how you'll be using these tools later on. So let's say that you've identified an investment and you're forecasting the cash flows you expect to get from this investment, and you expect it'll give you $400 in the first year, $800 in the second year, $500 in the third year, $400 in the fourth year, and $300 in the fifth year. Okay, so now what you want to do is, let's say that you want to figure out what is the maximum price you would be willing to pay for this investment, assuming that you want to earn at least a 9% rate of return. So that 9% becomes your opportunity cost. So you're going to be discounting at 9%. And we've got to take each one of these individually back to time period 0. There isn't any shortcut. So we have to take this 400, discount back 1 year at 9%. So I'm going to table 2. And you'll see that that discount factor is 0.917. Here's 9% at 2 years, and I multiply that to get the 673.60, and 9% for 3 years, 9% for 4 years, and 9% for 5 years, and I multiply to get the present values and sum them up, and I get $1,903 and a penny. So again, to frame this in an investment sense, this tells me that if I want to make sure that I earn a 9% rate, and I'm sure of these cash flows, okay, we're not going to incorporate risk into the analysis yet, that'll come later, and I'm sure of these cash flows, then I would not want to pay more than $1,903. I might give up the penny, but let's say I'm stingy. So $1,903 and a penny is the most I would be willing to pay for this investment. If I could get it for less than $1,903, then that means that's great. I would earn a rate of return higher than 9%, right? And if someone is charging me, say, $2,000 for this investment, I could buy it, but I wouldn't earn my 9% minimum rate of return. Okay, so now we're at the point where you can try using some of these tools, and there's 2 different ways you can do it. I'm going to go ahead and talk through the solutions here. So if you keep going through and doing it with me online, you might want to read the problem and pause here and then work through it, and then if you resume the recording on the next slide, I'll go through the answer with you. Alternatively, what you might want to do is, there's a handout posted on Sakai with the problems that we'll be working here. It's called Application of Present Value and Future Value Techniques. And so you can just print off that problem sheet if you prefer and work through all the problems, and then come back here to the video and see if you got them right. So I'm just going to make my way through the problems here. So let's say you want to purchase a house 5 years from now, and you want to put $20,000 down on the house. In order to save for the down payment, you plan to make equal annual end-of-year deposits into an account that pays interest of 6%. What is the size of the annuity you must pay? So this problem's a little different than the problems that we've done before. We're using the same formulas, I'm just using the formulas a little bit differently. Whereas before, in my earlier examples, we were finding the present value of the annuity. Here we have the present value of the annuity. The answer's there. We want to solve for the payment. So we know from this, we're making equal annual end-of-year deposits. We know that there's an annuity involved. So we know we have to use either present value of an annuity or future value of an annuity. So if you're confused as to which of the 2 formulas you should use, look at the info. You're going to have to plug numbers in, right? So look at the information given to you in the problem and see, what numbers you have that would fit into the formula. So we've got interest of 6%, and then we're looking 5 years out. So our interest factor is going to be based on that. And both of those formulas have an interest factor, so that doesn't help us. So the only other number that could give us a clue is this number here. and it says we want to put a $20,000 down payment on the house. So that $20,000 is an amount that we're trying to save up in 5 years, right? So it is a future value amount. So the only formula that has any place to plug in a future value number is future value annuity, right? If we're dealing with an annuity. So going to the next slide. All right, there's the problem restated again. And so if we go to the future value of an annuity formula, we're solving for the payment. All right, so we want to accumulate $20,000, and we want to do so over a 5-year period, earning 6% interest. So now I can just go to my future value interest factor of annuity table, table 3, and pull up this interest factor. And now I just divide the 20,000 by the 5.637 to come up with my payment of $35.47.99. So I'm going to round to $35.48. So what that's saying is if I save $35.48 every year for the next 5 years, at the end of 5 years I will have the $20,000 to put down as the down payment for my house. Next problem, it's another accumulation of a future sum type problem. We've got a retirement home that now costs $85,000. Inflation's expected to cause this price to increase by 6% per year over the next 20 years before you retire. How much will you need to save each year, assuming you can earn an annual rate of interest of 10%, to have the cash to purchase this home upon retirement? So this is really a two-step problem. The first step is you're going to have to find out how much the house is going to cost 20 years from now. And then you've got to figure out how much do you save each year to have enough to buy the house. Okay, so again, if you need to pause here, go ahead. And I'm going to go on to the solution. So here for the second one, first of all, how do we find out how much the house is going to cost 20 years from now? That's a straight future value problem, right? You have $85,000 compounded at the 6% inflation rate over the next 20 years. And so you can, again, use the table, or in this case, I use the calculator, and you find out the house is going to cost you, by the time you retire, it's going to be $272,603. So now this is the amount you have to save before you retire, and it says you want to retire in 20 years. So this is a future sum that needs to be saved up, so I'm using my future value of annuity formula again. And the future value that I want to save up is the $272,603. I think the real estate agent will probably drop the 50 cents. And then the payment is what we're solving for. And we know it's stated in the problem that we earn 10% interest over the 20 years. So here's the interest factor from your future value interest factor of annuity table, table 3. And so when you divide, we get a payment of $4,759.55. So if you put this amount away in that account that earns 10% interest every year for the next 20 years, you'll have exactly enough money to buy the house. Okay, here's another bank loan problem. This one's a little bit different. A bank offers to lend you $1,000 and you sign a note to repay $1,610.50 at the end of 5 years. What rate of interest are you paying? Okay, this problem is a little different than the others in the sense that, notice you're not paying an annuity. It's like a balloon loan. So you're borrowing $1,000 today to turn around and make one balloon payment of $1,610.50 at the end of 5 years. So that knocks out any of the annuity formulas because there's no annuity in here anywhere, which leaves us then with either present value or future value formula to use, the straight present value or future value. So here you can actually use either one. The present value and the future value formula, those are actually interchangeable because one's just derived from the other. One's the inverse basically of the other. So you could use either formula to solve this problem, and you're just solving for the interest rate. So on the next slide, which I'll switch to in just a second, I will show you how to do it using both formulas. So if you used future value, you'll see how it's done, or present value, and you can check your answer. Okay, so here I've got same problem. So if you use the present value formula to solve the problem, the present value amount that you plug in is the present value amount in the problem, right? It's the amount that the bank is loaning you today. So that's your present value. The amount that you're paying back in the future is your future value. And then you're borrowing for 5 years. So you plug that in. So now what I would do is take this $1,000, divide by 16,1050, and here I have my present value interest factor at year 5. So I go down into the body of my table, I go down 5 periods, move across the body of the table until I see 0.621, and you should find it right underneath the 10% column. All right, and that tells us then that our interest rate was 10%. If you use the future value formula to solve it, that's fine. Everything's just flipped, right? So the future value is the amount we're paying back. Here's our principal amount in the beginning. Just be sure to go to the future value table, table 1, and then you do the same thing. We divide here, and we have an interest factor of 1.611. And so now we go to table 1, go down 5 years, move across the body of the table till you see 1.611, and you'll find it right under the 10% column. So it didn't matter which formula you used, either one should have gotten you the answer of 10%. Okay, here's another bank loan problem. A bank offers to lend you $25,000 to buy a home. You have to sign a mortgage calling for payments of $25, $45, $16 at the end of each year for the next 25 years. What interest rate is the bank charging you? Okay, here we clearly have an annuity, right? You're making $2,545.16 payments every year for 25 years. So we definitely have an annuity. The question becomes, do we use present value annuity or future value annuity? So think about that and try solving the problem. And we'll go to the next slide. So if the bank offers you $25,000 to buy a home, that's a present value amount. They're giving you that amount of money now. So you don't have a choice but to use the present value of an annuity to solve this problem, because in the future value of an annuity there isn't any place for a present value amount. So here's my present value of the annuity is the $25,000. The payment is given to be $25.45, and we know that it's a mortgage that is 25 years out. So we solve for the interest rate. And keep in mind, we've got to go to table 4 now, our present value interest factor of annuity table. So when you divide, your present value interest factor of an annuity is 9.823. And if you go down, drop down to 25 periods and move across the body of the table until you see 9.823, you'll find it just underneath the 9% column. So the bank is charging them 9%. Okay, this one's a little less intuitive, but see if you can figure it out. You're wanting to find the average growth rate of this cash flow stream. So the assumption is you invested, let's say, $12.50 a year in year 1, and now it's year 5, and that $12.50 has grown to $15.20. So what is the average growth rate for this investment? Well, here's what you can do again. You would use either the present value or the future value formula to calculate this. Again, it doesn't matter since those two are interchangeable. This one, like I said, is a little less intuitive. You had to kind of know what to do. But what you would do is the amount that you started with, the amount you invested in, or invested with in the beginning, is always the present value amount. and then what it grew to is the future value amount. So if you use the present value formula, we started with 1250, it grew to 1520. If you use the future value formula, it grew to 1520, but we started with 1250. But just make sure you go to the correct table that goes with the corresponding formula. Now, the other thing that may have gotten you is you may have had 5 years here instead of 4, but, and this was a little tricky, I guess, but you don't have 5 years of growth here, right? Growth occurs in between years. So if you invest $12.50, say at the end of year 1, then you'll have growth till the end of year 2, growth again to the end of year 3, growth again to the end of year 4, and then to the end of year 5. So you really just have 4 years of growth. And even if I invested at the beginning of each year, you know, by the beginning of year 5, I would still just have 4 years of growth. So n is equal to 4, not 5. So now you just divide and go to the appropriate table and you know, go down 4 periods, move across until you see 0.822, or if you're using the future value table, table 1, go down 4 periods and move across until you see 1.216, and you'll find them both right underneath the 5% column. Okay, this problem I actually didn't talk to you about, but just see if you can figure it out. Perpetuity is an annuity that lasts forever. Okay, so you own a security that guarantees you $1,000 per year for as long as you live. You have an opportunity to invest the money at a guaranteed rate of 10%. If I wanted to purchase the security from you, what would be a fair market value? So assuming that you didn't want to rip me off, okay, and I wanted to purchase that perpetuity from you, and given the facts there, what would be the value of that perpetuity? Okay, see if you can figure that one out. All right, the value of that perpetuity is actually the perpetuity payment divided by the interest rate. I like to throw this example out oftentimes to my undergraduate classes because I'll ask them, I'll ask them if I offer them $10,000, would they give it to me? And most of the students will shake their heads no. But actually $10,000 is the value of that perpetuity. But a lot of times people think in terms of, gosh, $1,000 a year, every year for the rest of my life. They think it's got to be worth a lot more than $10,000. But if we follow the assumptions given in the problem, if you take the perpetuity payment and divide by the interest rate, we get the $10,000. So think about it. If you take that $10,000 that I give you today and put that back into your account that earns 10% interest, how much can you withdraw in interest now every year forever without ever touching that principal? And the answer is you would be able to withdraw $1,000 a year every year without ever touching that principal. So you would have recreated that $1,000 a year perpetuity by investing this $10,000. Of course, again, we're assuming that 10% is guaranteed, but we'll get into risk later on and look and see how we deal with that. Right now, though, we're assuming no risk. Well, thank you. That concludes the discussion on the time value of money, and I encourage you to move on to the next lecture and try some of the problems that I have for you just for practice purposes. So have a good rest of your day. Thank you. Bye-bye.